We're going to keep discussing the effect of magnetic fields on moving charges. In the previous topic, we talked about the direction of that force, but we didn't say anything about how large the force would be or what it depends upon. It turns out if you go and do some experiments, which of course is what we should all be doing, you find that the size of the magnetic force onto a moving charge particle depends upon a few things. It depends upon the size of the charge. The more charge, the larger the force. It also depends upon the size of the magnetic field. A large magnetic field gives a larger magnetic force on the moving charge. It also depends upon the speed that the charge is moving. And it turns out importantly that that's the speed the charge is moving across the magnetic field lines. If the charge is moving along the magnetic field lines, it feels no force at all. So we can now write down the size of that force on the moving charge will be the force F is going to equal the size of the charge Q times the size of the magnetic field B multiplied by how fast the charge is moving across the magnetic field lines. Now, here's an example that will show something interesting about the direction and the size of this magnetic field force on the moving charge. Here we have a magnetic field that's pointing into the page. Now, because everything's at right angles here, almost always we've got to choose one of the directions to be into or out of the page. So in this case, it's the magnetic field pointing into the screen. Those little X's you see there, you can think of those as being the back end of the arrows pointing into the screen. Our positive charge we have here is going to be moving upwards into that magnetic field, for example with speed v. Now as it enters that magnetic field, you can use your right-hand rule, it's good practice, to determine what the direction of the force will be. And if you do it correctly, you'll find that the force on the charge is going to be off to the left. Now, that force is at right angles to the direction of motion. If you go back and think about what we discussed in our motion module, that means that force can't increase the speed or decrease the speed. All it can do is change the direction of the charge. And of course it will deflect it there slightly off to the left. So our charge will now be moving upwards and slightly to the left. But now that our charge has changed the direction it's moving, the direction of the magnetic force changes as well. It's always at right angles to the velocity. So now at this point, the force will be in a slightly different direction. For example, in that direction. And so now our charge will be deflected a little bit further off to the left. You go and look at this process as the charge changes direction because of the force changes direction. And what you find is this constantly turning force so that our charge would in fact do some kind of circular motion in the magnetic field. So magnetic fields can act to steer charged particles. They don't speed them up or slow them down. An electric field can do that, but we can steer charged particles using magnetic fields. And there are some examples of that. In those very large particle accelerators that are used to do high energy physics experiments, they keep the particles moving in a circular path using very large magnets. Another example are the northern lights and southern lights, the aurora that you can see in the sky at high latitudes. What causes those northern and southern lights are charged particles streaming in from outer space colliding with the molecules in the upper atmosphere. But why do those streaming particles only choose to land at the north and south pole regions? Well, they don't choose to only arrive there, they arrive all over the Earth. But the Earth has a magnetic field associated with it. In fact, in some sense, the Earth looks a bit like a bar magnet. And when those charged particles come streaming in from outer space, they start to spiral around those magnetic field lines. The Earth's magnetic field actually protects us from a lot of the harmful charged radiation from outer space. But as these charged particles spiral around the field lines, they arrive when the field lines enter the atmosphere in the regions near the poles. Now we're going to move on and think about what about charges that are moving in a conductor, an electric current? Well, of course, the charges will still feel a magnetic force if they're moving across magnetic field lines. In this example here, we have a wire moving across the screen with a current travelling from left to right. Remember that current is the motion of charged particles. In particular, it's the direction that positive charges would move. We can one more time use our right-hand rule with our thumb in the direction that positive charge is moving, that is the direction of current, our fingers of our right hand into the screen, and we'll find there's a net force on this wire that points up the screen. So a current carrying wire in a magnetic field can in fact be moved along by the magnetic field. There's a magnetic force on it. And if we were clever and designed our wire the right shape and had everything working so that we could make our wire move in the right direction, we could actually use this idea to build some kind of motion device. In fact, that's what we do when we construct an electric motor. In the next topic, we're going to be discussing how we can make magnetic fields from moving charges, in particular electric currents.